afternoon, everyone. I'm Stan Lebach, and I'll be talking to you today about the underwater acoustics part of this. And I know some of you are very familiar with it, but probably a lot of you have never had to deal with acoustics. So I'm going to try and use the proper terminology and keep the jargon and confusing words to a minimum. But if I should use a term that bothers you or you don't understand, feel free to jump in, and I'll try and make sure that I clear that up right away so you get a better feel for what's going on. After I do a brief introduction on underwater acoustics and a little bit about sound in the Arctic, Mary's going to talk about how that affects the marine mammals that are there. So she's the biologist among us here. All right. Page down. I can just do it there.
There you go.
The first slide that I have up here is a slide that appeared, this figure appeared in National Geographic about 4 or 5 years ago, and I like it because it gives you an idea of what's going on in the ocean in a bigger picture. Not only do you have all kinds of acoustic sources out there, everything from whales to shipping to lightning strikes and wind and wave and rainstorms, but you also have a feel from this of the difference in frequencies that these different things produce, and also the fact that everything, all these sounds that you hear and the ambient noise that you would hear in the ocean, or the contributions to that from these sources, are range dependent. How far are you away from the thing that's making the sound? And this gives the feel of that it's the ocean, it's expanding. I will talk in general about general kind of ocean acoustics and propagation. Then we'll talk specifics about some of the things in the Arctic towards the end of my discussion. But at first, we'll just talk in the general terms. Okay. One of the things that's often talked about in the ocean is the ambient noise. And this curve was something that's put together by Seish, and I'm using it and my red writing here about using this with extreme caution because really it's kind of a mismatch of a lot of different things. It combines on the bottom part of it where you see seismic, shipping, surface waves, thermal noise. Those are things that are typically in the Wentz curves, or the curves that are used to identify noise in the ocean. But overridden on this are specific sources of a lot of different things that are contributors to the noise in the ocean. Not only the animals and the lightning strikes and a lot of different sonar systems that exist. The purpose of putting this together is to give you a feel that a lot of the sources that we use and that are used by man, or that are sounds that are produced by man as byproducts of our activities, like shipping noise, the cavitation off of the propellers there, or the mechanical equipment noise, overlap in frequency, which is the X or the bottom axis here, and can be loud enough if you're close enough to them, and which is the Y-axis, to affect the animals that are there and everything that's going on around them. We are used to this in our own world. We know that, the distant train, it's not a problem, but when you're 5 feet away from it, it's very loud and it's overriding everything that's going on around you as far as your hearing. This gives you a feel for that, okay? The basics of underwater acoustics, most often when people think about energy and waves, and you think about waves, you think about the kind of waves that you see on the ocean. Surface waves, particle motion waves that you can see visibly. That's not what acoustics is in the ocean. What the acoustics and underwater energy transmission in the ocean is the compression, the closing together of the particles of the water and the rarefication, the spreading out of them. Just like that little bulge in the slinky where all in the picture shown here, where all the coils are together, and that's actually propagating back and forth, right and left between the two hands. In this case, the places where there's high density of particles equates to a high pressure, and that equates to the black bands up here. So this is what you would see as a repeating signal coming through the water, how it would be perceived. I wanted to put just a general slide in of, why we have to consider this and why we think about it. And the main point of this slide is to show you that, yes, there are sounds that we produce, just like the cavitation coming off of propellers, that are not useful to us in terms of we don't deliberately try to create them. But for all the sonar systems that we do use, they do have a very important purpose. Everything from being able to see what's on the ocean floor, like we can with the upper portion of the slide here, the side scan sonar, which lets you basically see what's on the ocean, and you can penetrate into the ocean's bottom to find cables or pipelines, or if you use the right equipment, the bottom half of the slide showing you what an air gun can do to look at the structure of the sediments underneath and what has the potential to carry or to bear oil and gas or other materials that will be of interest to man. Each of the sonars has a unique set of properties of frequency, directionality, duration of the signal to try and fine-tune and capture these pictures. And they're not interchangeable. Each of them, just by looking at these two sonars, you can tell that there's a huge difference. For example, the air gun, for most of those frequencies, you would hear that. That would sound like a loud bang to you. The side scan sonars are 100 to 500 kilohertz. Human hearing only goes up to 20 kilohertz. So that would mostly be above our hearing range. We wouldn't even be able to see that or hear that. So this is why this is important. And this kind of activity and the use of these kind of systems will increase as mankind increases its use of the Arctic. Some basic terminology. There are basically two types of sonars, a passive sonar and active sonar, and both are important for marine mammals and for all the activities that we use sonars for. Passive is just that, that's listening. In this case, you have a sound source, so identified by the red dot, and a receiver. Think of this as someone speaking and your ear is the receiver and the sound coming to you. You have some source level, SL, that suffers some transmission loss on the way there, and you get a receive level. Active sonar is a little bit different. These are the things that are used by bats to find bugs or dolphins to find fish to eat, or a lot of our sonar systems. In this case, you have, there are different kinds, but in this case, the source and the receiver are co-located at this speaker. There's a sound that's propagated into the water, shown as the red lines here. It bounces off of whatever the target is. That can be a fish or the ocean bottom itself or any number of other things. And then the echoes come back, and that's the green line, that come back to the receiver. And in this case, you have two sets of transmission loss. A lot of what I'm going to talk about for a few minutes here is going to be that term, the transmission loss term, the TL term. And that's what's one of the main ways that the environment and how the environment is affected by what sounds we put into the water. Okay. As a big picture, this is to give you an idea of the kind of things that happen in the ocean. This is a sonar, a model run. It's a parabolic equation model propagation prediction of a sonar system operating off of Southern California. In this case, the little red dot up to the upper left is where the source is, and it's propagating a signal out horizontally that is going towards shore, towards the shallow water. The white line at the bottom here indicates the ocean's bottom. The sound actually bends down, refracts downward, and hits the ocean bottom and bounces off the bottom and slowly works its way in the shore. I wanted to show you this, and this is what's typically called a field plot. It has a few other names, but it's on the x-axis, it's range as you move into shore, and in the y-axis, it's depth. So even though you have a source that is near the surface and very loud, you can be fairly close to the surface, this area, this black area, and not hear it even as well as you could 50 miles away, even though you're 5 miles away, because of the way the sound propagates through the water. The point of that is that I don't want you to default to human hearing and what we hear and see in our normal lives. Normally, you think of my voice coming straight from my mouth or the speaker right directly to your ear in a straight line. And in the ocean, that's not the case. There's a lot of bending, or what's called refracting, in the ocean, and a lot of echoes and long distance propagation. Okay. We'll get back to this slide, and I'll point out a few things about it a little bit later after talk about some of the terminology. The simplest model in the ocean, and for acoustics in the ocean, is that you have a source, the sound propagates outward from it in a straight line until it hits something and it bounces. If it's the ocean surface, because there's such a difference in the density between the air and the water, all of the sound reflects off of that ocean surface and continues on. Again, this is, in a very idealized case that all the sound is reflected, that the ocean surface is that flat, and any other number of things that can interfere with that. In the idealized case for the ocean bottom, some of the sound actually propagates into the bottom, and that would be this transmission line here, as opposed to some also reflecting off. You can see that in the previous slide. Can you move back up? You can see that in the modeling is accounting for that here, in that some of this color actually goes into the bottom. It's below the bottom. So this model has includes some of the parameters for the sound and sediment in the bottom, and shows that sound is actually penetrating into the bottom before it typically returns back out to the water column. Okay, that's a very simplified model. The one other component of this that happens is the spreading of the energy. Think of a sound that's produced by this source, and it's on a sphere, in this case, an idealized sphere, and that sphere just keeps getting bigger and bigger. And the energy hasn't changed, so the energy is actually spread out over the sphere. And that's the way that would be identified as a transmission loss is showing as spherical spreading, which is a 20 log of the range. It's basically the surface area of that sphere. Eventually, the sphere starts to hit the ocean surface in the bottom, and it really kind of becomes a cylinder. And so you'll get cylindrical spreading, and that's what you would see here. That's the main way the energy is being spread out in a geometric form. That's the idealized case. One of the major issues with and components of that spreading and things that you have to consider in the ocean is that really the acoustic wavefront does not go out in a straight line. It's constantly refracting or bending. And the thing that causes and is the driving force behind that bending is the speed of sound in the water. I give a simple case here, a simple example to show you that a wavefront will actually bend. In this case, you have an incident wave. It's this blue line here with the red. And in this case, a simplified case, you have the speed of sound in the blue is half of that in the green. So in any given time unit, you'll move one red unit while you're in the blue. If you go into the orange, you move twice as far. And you can see here with the simple diagram that very quickly this wavefront has gone from moving in this direction to moving horizontally. This happens continuously in the ocean, and it has the effect of constantly bending the waves, the acoustic waves through the ocean. And it's controlled by the temperature, salinity, and pressure in the ocean. I always like to say sound is really lazy. Given a choice, it'll turn, the wavefront will turn, as you can see what's going on here, it'll turn towards the slower sound speed. Give you an idea of propagation and of rays in the ocean, this is not atypical. The sound here is trying to avoid the faster, deeper speed, so it bends away from that, reflects off the surface, and continues on. That was a very simplified case. The reality is the ocean's temperature and salinity profile is much more complex. And on the left side of this figure shows what the complexity of that. You have an area near the top that's controlled by the seasonal heating and cooling. You can see the 4 seasons here and variations of that. Some part of that energy and that heating of the water column penetrates down into the main thermocline, which keeps it slightly warmer than the rest. And as you go deeper, the water gets cooler and cooler until you're near, 30, 32, 35 degrees, in which case then what drives it is just that the pressure of the water on top of it is compressing the water molecules and making the speed faster. So speed slowly increases. That gives you an idea of what's going on. So you can imagine some of the things that happen in the ocean. If you're near the surface and you have that same kind of a slope that we saw in the previous slide, and you have a source, all the energy is going to try to stay up in that, what's called a surface duct. It's slowly bending away from going very deep, and some of it will be trapped in a surface duct. If the source is deeper, the equivalent of being about 1,000 meters deep here, you're near the sound channel, which is the slowest speed in the water column, then the sound will be constantly trying to bend to stay in that water column. And that's what's happening here. It's showing the limiting rays on propagation. This is what allows humpback whales to talk to each other and to hear the calls from thousands of miles away. Some of that, the energy from their calls gets trapped in this because they may be 1,000 meters deep and it can propagate that far. Two other types of propagation that are common is convergence zone. If the water is deep enough, the sound will actually go down somewhere between 12 to 19,000 feet, 3 to 6,000 meters, and actually because of this keeps getting faster and faster as you go deeper and deeper. If you go deep enough, the sound will actually turn back up, and that's what happens here. So if you make a sound, some portion of it will actually bend down, refract down towards the bottom, right, to get away from the high speeds up here, and then it slowly starts to turn back upward. And eventually will come back to the surface roughly 35 miles away from where you started, bounce off the surface and do it again. This is what drives a lot of the ambient noise from distant ships. So you think of the Atlantic Ocean with 5,000 or 10,000 ships in it. Those ships, even though they're far away, their sound is trapped in this kind of a propagation pattern. And so even though you're very far away, you can still hear them and they have a tendency to combine. The final one I want to talk about and just point out is the Arctic. And this is showing that typically in the Arctic is a truncated kind of version of this sound velocity profile. A lot of the time the Arctic is ice covered, and so it's 32 degrees or less, and it doesn't warm up very much in summer. So you really don't have this upper thermocline. You really just have the lower part of this. So you get the same effect as this. It's constantly bending up towards the surface, or constantly, as if you're trapped in a duct, you're constantly bending towards the surface. And that's what you see here. The sound in the Arctic constantly bending upward. And occasionally it'll hit the bottom, but a lot of it is directed upward. And that will drive how the sound propagates in the ocean there. Okay. A couple other just little things to consider in advancing from the simplified propagation case. We talked about sound hitting the bottom and reflecting off. That's in a perfect idealized mirror-like bottom. The reality is that you have a beam pattern that's produced by the sound reflecting off the bottom with some amount of diffusion scattering, and that's in a perfect idealized case. And then if you even have a rough bottom, it even further distorts the signal. So you do get some sound that's scattered backwards. Also, we also talked about, we've ignored the fact that as sound propagates through the water, some of its energy is lost. It's absorbed by the water itself, or scattered by things in it, like little air bubbles or little fish or any number of other things. But the water itself actually absorbs some of the energy from that. And so there is a frequency-dependent composition of the absorption of energy as it propagates through the water. So going back and taking a look at that figure that I showed previously, show you a few things that are going on. First of all, you have transmission into the ocean bottom here. You can see the reflection. It is reflecting and moving inward. So there is a reflection off the ocean bottom. That's what produces this beam. Refraction, believe it or not, this source was the Navy's low-frequency active source. This was propagated horizontally. Picture this as a flashlight pointing horizontally, and within 5 kilometers, it's been refracted downwards, directed towards the bottom. That tells you the sound speed has that much effect on refracting the water. And then you have absorption. It's a little bit hard to tell, but what's happening here is because of the way the sound has been reflected off of the bottom, there are limiting rays, and a lot of these rays are not actually hitting the surface. They're bending back downward towards the bottom again and again, and you can see the general shift of the loss and the lowering receive level, higher transmission loss as you move into shore because of absorption in the water. So that kind of demonstrates that. The other reason I put this on is, in a way, you can look at this as, if you were to flip this top to bottom, this is kind of what would happen with propagation in the Arctic. The sound will be refracted. Remember, we talked about it being refracted and made to go back towards the surface. So imagine if this, what's the bottom here is really the surface, and so the surface were at the bottom here, and these could be ice ridges or other components or things that the ice would present, a rough bottom. So as the sound from a source in the Arctic, if there's ice present, when it gets under the ice, it starts to hit these ridges and starts to lose energy and scatter. And so this is the same kind of thing that happens in the Arctic. Okay. So what's going to happen with all this as the Arctic slowly warms up? Well, there are a few things that happen. A lot of different mechanisms, and I'll leave it for the oceanographers among us to say what's going to happen macroscopically with things like the ocean currents moving or changing, or land flooding and things like that happening. But from the acoustic point of view, a few things are going to happen. The first is that just our mere presence alone is going to affect a lot of the components, the acoustic components. You will get a lot more noise in the Arctic because of increased shipping. There'll be new routes, new sources of noise that need to be there to support the new shipping routes, like icebreakers and piloting ships and rescue facilities, ports, all that kind of thing. So all those things are adding ambient noise and more ships into the mix. So the ambient noise would be expected to go up just from that alone. You would also expect increased energy exploration, and that has a set of noise all itself, increased military activity, increased construction. All of those man-made activities add to the ambient noise. In the world of acoustic impacts, generally they break them up into 3 or 4 different categories. First of all, there are some amount of direct impacts. Level A, which is in the MMPA, Marine Mammal Protection Act, it's U.S. law, is injury, and then level B is harassment. We can talk about that more later, or Mary will probably touch on it some. But so you can have direct impacts from all of these extra sources, but then there are also considerations that are going into behavioral changes, chronic and cumulative effects on animals because of the sounds that are there. And you would expect that in general, the increased presence would degrade the soundscape that exists there. Okay. From the acoustic point of view, we'll leave those macroscopic things to the physical oceanographers and their predictive models. But there are some things that you would expect to happen with water temperatures warming. If you remember, I talked about the Arctic waters primarily being pretty close to 30, 36 degrees, even at the warmest, and there's very, very little surface warming. As that changes, what you would expect is that you'll get more of a sound velocity profile like was seen in the normal oceans. And so what that would cause is that in general, and be concentrated in some places more than others, but you would expect that instead of making the sound bend towards the ocean surface, it would propagate more like in straight lines, in what's called an isovelocity profile. So when that happens, you have less interactions, or you tend to have less interactions with either the surface or the bottom. Like I showed in that one propagation where the sound was kind of driven into the bottom because of the sun profile. You'll have less of that driving it into the bottom. It'll just propagate out straight. And so in general, on average, you'll have less interactions. That means, and that sounds like it's a good thing, but really it's not. When you have less interactions with the boundaries, the surface or the ocean floor boundaries, you have less transmission loss and less scattering of the sound, so you have louder sounds propagating further. So that would increase and potentially further hurt the soundscape that's there and the potential for injuring animals. Okay. Let's see. Also, ambient noise. You would expect that to help ambient noise go up a little bit. I think that covered most of those ideas. You can look at the wording here for anything more. But are there any questions at this point before I turn it over to Mary? Either you're all asleep, or you've all hung up because I'm boring. So, all right, I'll turn it over to Mary now. I'm sorry. Go ahead.
Steve, I had one quick question. The fact that you don't have such a strong upward refraction in a case where there was less of a gradient in temperature would also mean that there would be less concentration of sound near the surface. So transmission loss might go up over or down over the entire ocean. Near the surface, at least, it would increase. So you would expect lower sound levels near the surface. So I thought I'd just clarify that one point.
Yeah. And that was the other thing too, is with warming, you'd have less ice there to help. Ice, when it's not crunching on itself and making a lot of noise, it has a tendency to deaden the sound some. So you'd have probably more, I would think, more interaction with ice noise because it's going to take bigger fields to grow and produce that and break it up, and then less there to deaden the sound. So.
Sure.
Okay. Thank you.
Okay, now we're going to switch direction a little bit. Can people hear me okay? Hope so.
Yes. Yes.
Thank you. I have a lot softer voice than Stan, so I wanted to check. We're going to switch focus a bit here and talk about how marine mammals use sound from a behavioral aspect and how they can be impacted by anthropogenic noise in the environment. A couple things to keep in mind. Marine mammals tend to be very long-lived and slow to reproduce. This means that populations recover more slowly from events that result in decreased reproductive success, and that decreases in reproductive success may not be evident as quickly as they would be in a quick turnover population that has large litters, say, as opposed to one calf or pup at a time. This is very important to understand that the effects that disturbance and disruption of normal behavior patterns, including those from sound, may have on individual fitness and reproductive success may not show up right away. So as managers, that's something we have to keep in mind. So the more prominent species in the Chukchi and Beaufort Seas that you hear about most often are bowhead, beluga, bearded and ring seals, walrus, and polar bear. In part because they're important subsistence species, but there's others that occur there too. There's also orca, harbor porpoise, gray whales, fin and humpback, minkies, spotted and ribbon seals. Orcas, fins, and humpback whales are appearing more frequently in the Chukchi Sea as the open water period becomes more extended, but they aren't seen really commonly. And hunters are reporting seeing harbor porpoises more frequently than in the past as well. Most of these species move north and south with the edge of the sea ice, migrating into the Bering Sea in fall as the sea ice expands, and then many take advantage of the nearshore spring lead system as they move back into the Chukchi Sea in spring. I'll just mention a couple of areas. The Hannah Shoal area is particularly important to walrus, and the area off Point Barrow is an important feeding area for bowheads in spring in many years. So focusing on Pacific walrus first. Walrus are highly social, and they use sound to stay in contact with one another as they migrate or rest on the sea ice and feed in the shallow waters off the continental shelf. You rarely see walrus alone. They usually appear in very large groups like this. They feed primarily on benthic invertebrates, mollusks, clams, marine worms. Like most marine mammal species, they're long-lived, they're slow to sexually mature. A female will only have a calf every 2+ years, and they have a long lifespan. They make a variety of noises. Males attract females during the breeding season through elaborate displays that include chiming sounds and bell-like sounds that have been described as singing. Both sexes also make a rapid staccato clacking noise that carries very well underwater, and young calves have a tendency to make a sound that's more like a higher-pitched yelp. A disturbance for walrus may result in separation from the herd, separation of mothers and calves, or stampedes, and younger, smaller animals are really vulnerable in stampedes. If a disturbance event occurs that chases the group off at once, it's not unusual, especially at shore-based haulouts, for calves to be injured or killed. Underwater audiograms for walrus show a strong similarity to those for eared seals and are also similar to the ears of other carnivores such as polar bears. Walrus and eared seals have slightly better in-ear hearing than ice seals, or other phocids or earless seals. One interesting thing about walrus, they also have an excellent sense of smell when they're hauled out, and they rely on the sense of smell to avoid predators. When both hunters and researchers have found that when you're approaching walrus, you can get pretty close in a small boat, even though the boat's noisy, as long as you're approaching downwind. If you're upwind, they react really quickly. And hunters say the same thing about bowhead whales. They have a really good sense of smell, and the smell of the boat, they may react to before they even hear it. Wait a minute here. Sorry about that. Ice seals, on the other hand, are largely solitary. It's not unusual to see a number of individuals on a very large ice pan, but they don't appear to be interacting, and they respond to disturbance individually rather than as a group the way that walrus do. Communication for them is particularly important during the breeding season when they're looking for mates, and possibly between mothers and pups for the few months before the pups are weaned. I should have said with walrus, calves stay with their mothers for several years. They're very dependent. Their behavior is primarily learned. If they get separated from their mother, they're not likely to survive. Whereas for most ice seal species, the pups are only dependent on their mothers for a very short period of time. Most of their behavior is instinctive, and they'll do just fine if they're separated from their mom once they're weaned. The variety of sounds that ice seals make is really amazing. I wanted to include some here, but I sort of ran out of time. It's easily available on the web through the DOCITS website, Discovery of Sound in the Sea, and if you're interested, I highly recommend listening to some of the calls. They're really, really interesting. Beluga are very gregarious. It's not uncommon to see them in groups of thousands. They're generalists. They prey on fish, squid, crabs, clams, but in the Arctic they tend to prey primarily on Arctic cod. They generate sound with their nasal system, and in addition to using sound to communicate, beluga and other toothed whales rely on echolocation to find prey. This is really important because it means that sound that interferes with their ability to echolocate interferes with their ability to feed. Their hearing is highly directional, enabling them to locate objects in three-dimensional space. And for beluga whales at depth, sounds are conducted primarily through their jaw rather than an eardrum. And the significance of that is that their hearing is not attenuated at depth. There's some recent studies that are really interesting to me that indicate that beluga can alter their hearing when exposed to very loud sounds. They've trained captive whales so that they'll play a stimulus and then play the loud sound, and the beluga can actually dampen down their hearing by several decibels prior to the loud sound. That may be helpful to them and provide some small level of protection from loud noises. Bowhead whales are usually alone or in small groups, but they tend to communicate with one another across vast areas. So even though you may be seeing a few at a time, they may still be communicating among one another. Like other bowhead whales, they're very vocal during migration. They have long, complex songs which may change over time, and they have a large repertoire of calls. The echoes of these calls may be used to help the whales navigate through the ice as they migrate. Both bowhead and beluga whales may respond to anthropogenic noise by reducing call rates, deflecting away from sound sources, spending less time at the surface, and reducing respirations. Most of these behaviors come with an energetic cost. If there's sufficient noise to mask the sound of ships approaching, slow-swimming whales such as bowheads may also be at an increased risk of collision. Passive acoustic monitoring studies in the presence of seismic operations in the Beaufort Sea have shown an increase in call rates as the seismic sounds are first encountered, followed by a decrease in a complete cessation of calling when the seismic sound levels reach above approximately 160 dB. It's thought that baleen whales, including bowhead whales, probably have excellent hearing based on skull and ear morphology, but for obvious reasons it's not possible to get audiograms on large whales. Their ears seem to be designed for low-frequency hearing and sound levels that travel great distance underwater. Polar bears are generally solitary, although in the breeding season you'll see a few together, and when there's a large food source like a beached bowhead whale, they'll tolerate one another at those sites. They pretty much ignore each other as long as there's enough food. They have very sensitive hearing over a wide frequency range, but they rely primarily on their sense of smell to locate prey and potential mates. When in the water, polar bears swim with their heads and ears out of the water for the most part, so impacts from underwater sound is less of an issue when you're thinking of polar bears. However, polar bears may be impacted by the effects of noise if prey species are displaced in areas where the bears are hunting. They vocalize to communicate with cubs and to warn off conspecifics, but primarily they rely on the sense of smell. This is the most recent stock assessment from NIML, and I included it just because I wanted to focus a little bit on the fact that these are, for a lot of stocks in the Arctic, they're relatively small populations. And it's extremely expensive to do surveys, so we aren't able to do them very often due to the expense and the inaccessibility. So that makes it more difficult to track trends over time, which as a manager, that's an important thing to keep in mind as activity in the Arctic is growing more quickly, perhaps, than our ability to keep track of what's happening with the animals. This graph compares hearing among mysticetes, which are baleen whales, odontocetes, which are the toothed whales, and pinnipeds or seals, with a human's underwater hearing. Baleen whales, like the bowhead, have the best low-frequency hearing, while toothed whales and seals have higher frequency hearing. So this graph compares the sound levels, but it's based upon the sounds that the animals make, and it's grouped by family. You can see that earless seals have this broad range, as opposed to something like walrus and sea otters, where it's a smaller range of hearing. Well, a smaller range of calling, I should say, at least. So this graph relies on measuring the calls and noises that the animals make. A lot of hearing information is based on audiograms, but sometimes it's from just a few individuals. And there are a few different ways to measure audiograms. I think sort of the gold standard is when you have captive animals and you can use stimulus response experiments. But we have those for some species like beluga and walrus and some seals and sea lions, but they're based on relatively small numbers of animals, and animal hearing varies just like human hearing varies among individuals. In the wild, there have been more studies using evoked auditory potential. They've done it on beluga and polar bears and some other non-Arctic species, and this may provide an opportunity to get more individuals and a larger sample size. And for larger whales, we just rely on extrapolations based on skull morphology and the songs and the calls that they produce. So, especially since Dave's on the phone, the last slide and these two graphs are both from JASCO, so thank you, Dave. This is an aerial view of impacts. It's assuming a very loud sound source, such as an explosion or a very loud seismic circuit at the very center of that innermost circle. A lot of the sound sources in the Arctic may not get loud enough to cause injury or a permanent threshold shift. But this graph sort of assumes one that does. So the nearest sound source impacts could include a permanent threshold shift, which is essentially a hearing loss or soft tissue injury. The distance from each of these zones it's not a fixed point at all. Stan went into this in a great deal of detail, but the distance for each of these is going to depend upon transmission loss and the distance to the receiver, which in this case is a marine mammal, and the depth. As the animal gets further away from the sound source, you may get TTS, which is a temporary threshold shift. And you can think of this as being like you've gone to that really loud rock concert and your ears feel cloudy and stuffed with cotton for a few hours, few injuries. You're essentially experiencing TTS. The impacts of masking are the next sort of inherent circle as you move out. And that's basically that the received anthropogenic sound is blocking other sounds nearby. You can think of it as when you're in a noisy crowd and you can't hear your friends and you can't quite hear the traffic or what's going on around you. This has the potential to result in an increased risk of predation, an inability to locate mates or offspring, potential for increased risk of collisions among slow-moving whales, as I mentioned earlier, and a decreased ability to find prey, especially for species that echolocate. Probably the largest circle and the most often response that you're going to get are behavioral responses from animals that are furthest away from the sound source. This can result in decreased energetic fitness over time depending on the amount of impact or the number of times that they have to respond to sound. For example, animals may spend more time avoiding sound sources, which decreases the time spent resting or foraging. They may be forced to move to poorer foraging habitat or spend more time searching for mates and offspring. Cumulative impacts from multiple sound sources or stresses are difficult to assess. So when we think of behavioral impacts, it's not just the impacts to that one seismic sound source, but maybe there's 4 surveys that go through the area where they are, and trying to get a handle on how the animals are moving through these areas of anthropogenic sound over time and how it's impacting them is complicated and difficult. Sources of anthropogenic noise in the Arctic include aircraft, icebreakers, cargo and tanker traffic, oceanographic and wildlife surveys, seismic surveys, drilling operations, Coast Guard naval operations, tourism, and all of those things can cause acoustic disturbances and alter the Arctic soundscape. With the increased interest in the Arctic and the increased open water season, traffic is increasing now and projected to continue to increase, which makes for a more complicated, basically a noisier soundscape that animals have to maneuver through. This slide sums up anthropogenic noise impacts, which may result in acute impacts such as immediate physiological or behavioral impacts, can also cause low levels of ongoing stress due to the loss of acoustic habitat over time. Some industries, excuse me, the oil and gas industry, military operations, and the research field generally have defined marine mammal mitigation plans in place, such as the ones listed here. This is for oil and gas industry. And these can help to minimize some of the impacts to marine mammals. Marine mammal observers on board can help direct activity away from where marine mammals are, being aware of where the animals are migrating through, avoiding the spring lead system. All those things can help to minimize impacts. But I wanted to point out that so far other industries such as shipping, tourism, private vessels, they may not be as aware of the potential to impact marine mammals, and they may not be as involved in following mitigation measures, knowing what they are, as some of the other industries that are more established in the Arctic. Icebreaker tourism cruises are increasing and are both a very loud source of sound and a potential disturbance, and many of them advertise getting as close as possible to the marine mammals, so we definitely have some work with education and regulation to do on that front. Last, I just wanted to mention that new technologies are coming online which are making it possible to measure sound levels across broad soundscapes, including throughout oceans, and to begin to think about ways to address the cumulative impacts on a population as it moves between seas during migration and between different anthropogenic activities. So I think that's sort of, in terms of regulation and management, that's kind of the next steps to look at. Hey, we made it on time.
Thank you, Mary. Thank you, Stan. Are there any questions for them?
Hi, this is Francis. I have a quick question.
Sure.
Yeah, I was wondering, you mentioned about the belugas and I think bottlenose dolphins that can potentially adjust their hearing or dampen their hearing by, I think, to like 15 decibels or whatever it is if they have a warning sound. So under experimental gradation, that's work, but do you think that there will be, would there be do you anticipate there being some sort of a mechanism that could then be introduced in any kind of anthropogenic activities that could function like that, so they could actually anticipate it and therefore reduce their quote-unquote exposure?
Let me stand. Can we?
Go ahead. I'll answer.
Okay. Okay. So it appears to be a voluntary response on their part, and I can certainly imagine that if they're, say, in the vicinity of a seismic operation and it's coming closer to where they are, that could function as that sort of warning sound. They appear to be able to do that naturally when they're impacted by large sounds, but that's you know, that's speculating and based on what we know so far about them. Pilot whales can do that too. I think it would be really interesting to try to figure that out if that's happening in the wild. I think it's not unlikely that it is.
Yeah. I just wonder if that knowledge from those controlled experiments could be used to develop some mitigation measures that would be, you know, to kind of give them a heads up that these loud noises are coming.
Yeah, I think that's an excellent idea, and I think the ramp up that seismic vessels currently do is designed to do exactly that kind of thing, but that's only one instance. And
there are other things like explosive removal of rigs and things. They do have looked at using aversion sounds to chase animals away from the area before actually setting off the explosive. But also embedded in the acoustic propagation, you can also get a little bit of what they call a precursor. Some of that energy, for example, that may go into the ocean bottom. If the conditions are right, you'll see the sound can actually move through the sediment much faster than it goes through the water. And so even though it's a small portion of the energy, some part of there's multiple paths of the sound getting from one point to another, and sometimes those other paths, like through the sediment or trapped in a duct, can give you a little bit of a heads up of, you know, milliseconds or so before the main loudest part of the pulse gets to you. So they call it a precursor, and then I've seen it in sonar systems, and it happens with air guns and things too.
Cool. Thank you.
Other questions?